In this lecture, we're going to focus on dangling pointers and show you how they can be bad. A dangling pointer is a pointer that is pointing to a valid address, and we have seen a few examples of this already. But in this lecture, we're going to focus on that and show you common solutions we can apply to these problems here. And dangling pointers are really bad. They are going to lead your programs to undefined behavior, and we have seen that that can crash your program many times. There are three kinds of dangling pointers we're going to look at in this lecture. The first one is a pointer that is not initialized. The second one is a deleted pointer. And the third case may come if you have multiple pointers pointing to the same memory location. And let's look at these cases one by one. Here we have an example of a pointer that is not properly initialized. This is P number 5. It is a pointer to int, and it is not initialized. It doesn't really point anywhere, and it is going to contain junk address. If we try to dereference it, we're going to get bad things to happen because we don't really know which address is stored in there, and putting something in there might lead to a crash. So this is something you need to watch out for. The second kind of dangling pointer that can really lead you to bad places is a deleted pointer. Here is a pointer, P number 1. It is initialized with dynamic memory, and we can use it. For example, here we are dereferencing the pointer and printing the value inside and deleting the pointer. After we delete the pointer, don't really use it before you properly initialize it with some kind of memory. If we try to do that, this is going to be undefined behavior and your program might crash. So make sure you don't do something like this. Another case is if you have multiple pointers pointing to the same address. And here is a simple example to drive the point home. We have pointer 3, which is pointing to dynamic memory here. We are using new int in our braced initializer, and we are putting value 83 in that pointer location. And here we set up another pointer, P number 4, and we initialize that with another pointer. And if we print these things out, we're going to get that they contain the same address and they contain the same value. We're going to see that. If we delete P number 3 and try to use P number 4 later, we're going to get problems because this memory has been deleted by P number 3, but P number 4 is still pointing to that. And if it tries to use that, it's going to be deleted memory basically, and we're going to get undefined behavior. So be sure you know these problems and try to avoid them in your programs. Okay, these are problems, but how do we solve them? Well, there are a few solutions. One is to always initialize your pointers. The moment you declare a pointer, make sure it is initialized. If you don't know what you can initialize that pointer with, put in null pointer first, and then you're going to put in an address later when you have a clear idea of which address you can store in. The second solution is to reset your pointers to null PTR after you delete the memory. That's the second thing you should do every time you call delete. That's going to give other developers or even yourself a chance to check and see if that memory location contains a valid address before you do that. And for multiple pointers pointing to the same address, you have to choose and make one pointer the master of the controller of the memory. And all pointers are basically going to be slaves, which can't release the memory, but they can read and do something with that memory. But they don't have the task of releasing that memory. And here is how you can apply solution 1, for example. We have pointer number 5, and we're going to brace initialize it. This is going to initialize it to null pointer. The other thing you can do is initialize the pointer with dynamic memory like we are doing here with P number 6. And this is going to put in the value, and we are going to be playing on the safe side. Now, if your pointers are initialized, developers have a chance to check your pointers against null PTR to see that they contain something valid before they use it. And if they see that it contains null PTR, they are not going to try and use it. And this is going to be very safe. For the second problem with deleted pointers, we are going to reset our pointers after we call delete. For example, here we have P number 7 initialized with dynamic memory and 92 is stored in. We can print it out or do things with it. When we delete the memory, we're going to reset it to null PTR so that other developers or even ourselves can check this memory against null PTR. And if it's different from null PTR, we can use it. If it's equal to null PTR, we're going to leave it alone and do something else. This is going to be very safe. If you have multiple pointers pointing to the same address like we have here, then you're going to have to decide which pointer is the master pointer and other pointers are going to be slave pointers. And before use, all the other pointers are going to check against the master pointer and see that it contains valid memory, because the master pointer has the task of deleting this memory. Let's go through this and see how this could work in practice. So P number 5 is our master pointer. We are setting P number 5 and initializing it with P number 8. We are printing things using P number 8. We can either use P number 8 or P number 9. This is going to work. But before we use the memory location, we're going to check against the master pointer. If the master pointer contains null PTR, we're not going to use this memory. If the master pointer doesn't contain null PTR, we're going to use this memory here. Okay, if you go down, you see that the master pointer is going to be releasing the memory. And if we try to use that memory after it was deleted, we're going to see that it contains null PTR and we're not going to be using it. This is something cool, and it is really easy to implement these safety guidelines in your programs. Now that you know about this, we're going to go to Visual Studio Code and show you this in action. Okay, here we are in our working directory. The current project is Dangling Pointers. So we're going to grab our template files pretty quick and put that in our project. And we're going to open this in Visual Studio Code. We are going to look at the first case of a dangling pointer, and this is a pointer that is not initialized properly like P number here. If we try to dereference it, we're going to get something bad to happen. So let's see that, and let's go down and say that program is ending well, just to know that we didn't get a crash, because a crash is basically going to terminate your program on the offending line. That's what it's going to do. So if the program works well and ends well, we're going to print this line here. Let's bring in GCC to build this program, and let's open a terminal so that we can run it. We're going to clear. The build was good, and we're going to run Rooster. You see that the program didn't end well. It crashed, and it crashed because we are trying to use uninitialized memory. When the operating system is going to try and run this thing, it's going to see, this guy is trying to modify memory that doesn't really belong to him. It is a rogue program. I am going to kill it, and it is going to be terminated on this line here. This is really bad. You should avoid these kinds of situations. So don't do this. We are going to comment this out and show you another offending thing we can do in our program. And that is using a deleted pointer. If you do that, you're going to get something bad in your programs. So here we have a small example. We have a pointer to int. We initialize this with a dynamic piece of memory, and we're going to store in a 67. And we can print this out. This is going to work pretty well. But we delete the memory down here, and we try to use it after we have deleted the memory. So the operating system is not going to be happy about this, because once the memory is deleted, it is no longer our memory, so we have no business dereferencing pointer 1 and trying to use that here. And we're going to get a crash, and this is something you should avoid. So let's try and build this and show you this in action. We are going to clear and run Rooster. And you're going to see that program is ending well, but in some cases it might crash. And hopefully this shows you the danger that these things might put you into. Sometimes your program is going to seem working fine, but sometimes when this memory that we are pointing to in P number 1 here is being used to do something really important by the operating system, you are going to get a crash. So you're not guaranteed to get the same behavior every time you run your program. Some of you might be saying, the program is working here, Daniel. Why are you making this such a big deal? Well, it is a big deal because you are not guaranteed to get the same results every time you run this program. So be sure you really avoid these kinds of situations. Let's try and clear and run the program again. Hopefully we're going to see it crash, but we're not. Okay, so let's clear and rebuild again. And see that we have better luck that time. Let's clear and run Rooster. It is going to end well, but you notice that we are trying to use a piece of memory that has already been deleted, and this is bad. Don't do this. Make sure you don't do something like this. We're going to comment this out again and show you another offending thing we can do with our programs. And bad things might happen if you try to have multiple pointers pointing to the same address, and that's what we have here. We have P number 3 and P number 4 here. P number 3 is allocating new space and it is pointing to it. We have an 83 inside, and P number 4 is initialized with P number 3. We can do that. So these two pointers are basically pointing to the same memory location. Let's run this and show you that. We're going to comment out this delete statement here and run the program first to really prove that they are pointing to the same addresses and they contain the same values. Let's build and run. We're going to use GCC for that, and we're going to clear and run roster, and you see that P number 3, the address is this and it contains an 83. P number 4 contains the same things. So let's see what happens if we try to delete using P number 3 and using P number 4 later to try and read stuff. This is what we are doing here. And we're going to see if the program actually gets to end well. We're going to build again. The build is going to be good. Let's bring this up and clear and run roster. And you're going to see that the program is also going to end well, but we are using a deleted piece of memory here, and anything can really happen. Okay, so you might get garbage, you might have really any piece of junk inside, or you might get a crash in some extreme cases. So this is really bad. Don't do it. Don't try to use a piece of memory that you have already deleted through a pointer. And these are problems you might run into in your programs if you try to use dynamic memory allocation. Let's look at how we can solve them. And the ultimate advice is to make sure you put a null PTR in a pointer if you don't know what that pointer is actually storing. Okay, let's go down and look at solution 1. Solution 1 is to initialize your pointer to null pointer every time. If you don't have a value you can put in, use null PTR. That's what we are using here implicitly, but we can explicitly put that in because it is good. And before you use a pointer, you have to check and see if it doesn't contain null pointer. This is how we do it. If pointer 6 is different from null pointer, we're going to use it. If it is equal to null pointer, we're not going to use it. And we're going to be playing on the safe side. And you're going to see that the program is going to end well here. If we have a null PTR inside, we can say else here and say invalid address. Okay, and the user is going to know that they are trying to do something really bad. So let's try and check against P number 5. So let's go and store a null pointer in P number 6 to really try this out and show you that we're going to get this warning if we try to use it. And we're going to build with GCC, and we're going to clear and run roster. You're going to see that invalid address, and the program is going to end well. And if we try to put this statement somewhere where we're not checking against null pointer, we are going to get a crash. So let's comment this out so that it's clear what it is we are running here. So if we run this, we're going to get a crash. We have seen that, but let's show this again and really highlight that we are solving the problem here. If we run roster, the program is going to crash because we are trying to use an initialized memory. But if we try and check against null PTR, like we are doing here, let's do that. We're going to be playing on the safe side because it's going to tell us invalid address and we're not going to get a crash and the program is going to end well. This is really cool. So let's try and do that again. We're going to build. The build is going to be good. We can clear and run roster and the program is going to end well. Okay, so if we have a value inside, we're going to get that. So let's put that in and say new int and put in an 87, for example. It doesn't really matter what we put in. So we're going to build again. The build is going to be good and we can run roster and you see that we are getting a value here if we are not storing null PTR in P number 6. And you can do the same checks against P number 5, but I think this is really enough. So this is one way you can avoid dangling pointers. The next thing we're going to look at is if we are using a deleted pointer. And again, the solution is to set our pointer to null PTR after we delete it. Here we have pin number 7. It has 82 inside. We are using it here and printing stuff out. We're going to delete it after we are done using it. And after that, the first thing we do is to reset it to null PTR. When we do that, other people or even ourselves have a chance to check it against null PTR, and we're going to know that it doesn't contain anything useful for our program. And if we do something like this, we're not going to run into all these weird problems, and our program is going to have consistent behavior across different runs. And this is really cool. So we're going to run this, we're going to get things printed out, and the program is going to end well because right now we are checking against null PTR. We can even be explicit in showing the warning here. We can say invalid memory access, and if you run this program, you're going to really know this. So let's finish this up. And we're going to build, and the build is going to be good. If we run this and run rooster, we're going to know that we are doing an invalid memory access after we have deleted the pointer. And this is going to save you from possible crashes that you might experience if you don't do this. So this is a second solution you might want to implement in your programs. And we're going to comment it out and show you how you can get away from the problem of when you have multiple pointers pointing to the same address. We are going to go down and put in the code. It is what you have seen in the slides, and it is really nothing new. So we have pointer 8 and pointer 9 here, and pin number 8 here is pointing to dynamic memory, and the value inside is 382. Pin number 9 is initialized with whatever we have in pin number 8, so they are going to be pointing to the same addresses here. But we have made pin number 8 the master pointer. So it is the only pointer that is going to be able to delete this memory location, even if we have multiple pointers pointing to that. Okay, so every time we want to use this memory, we have the option to check against the master pointer and see that we have some valid data inside. If it is null pointer, we're not going to use that, and we're going to be playing on the safe side. And this is really what we are doing here. If we run this, we're going to see that the program is going to end well. The build is going to be good. And if we run rooster, we're going to see that we get things printed out. We're going to go through pin number 8, we're going to print stuff. We're going to go through pin number 9, we're going to print stuff. And if we try to use the pointer after the memory has been deleted, we're going to get a clear warning that we are trying to do something really bad. And this is really what you should aim for in your C++ programs that use dynamic memory allocation and pointers. This is really all we set out to do in this lecture. I hope you know how you can avoid these problems with dangling pointers. We are going to stop here in this lecture. In the next lecture, we're going to see what can happen if this new operator fails to give you the memory that you want to allocate on the heap. And that's possible. Go ahead and finish up here and meet me there.